Hello, I'm Alan Adams, Chief Structural Engineer for the RAM Group at Bentley Systems. This is the first of two presentations on structural irregularities. In this presentation, I will discuss structural irregularities and how to identify them in a structure. In a subsequent presentation, I will discuss what needs to be done analytically and for design when a structure has one or more structural irregularities. Modern structures come in a wide variety of shapes and configurations. They are more functional, they are more versatile and accommodating of the intended use. They add interest, variety, and excitement to their community. Some iconic structures even come to be a symbol of the city that they are in. They also challenge the engineer. With today's computing power, more and more complex structures can be safely analyzed and designed, and that ability invites us to push the envelope to create even more complex and creative structures. Even the common office building is becoming more tailored to the client, with layouts intended to facilitate productivity and creative thinking, and with profiles making an architectural statement to bring attention to their brand. As structures have gotten more complex, and as these structures have been subjected to harsh loading conditions, we're learning that certain configurations are more prone to damage and failures. To protect against this, the building codes have become increasingly more complex. Codes now explicitly recognize certain configurations, referred to as structural irregularities, or similar terminology, and include extensive requirements for determining their existence and for abating their consequences. Determining whether or not the structure being designed exhibits these irregularities places a demand on the engineer's time, and if they occur, the codes often require analysis or design methodologies that are more complicated, demanding even more time and effort by the engineer. In this webinar, we will discuss code requirements related to structural irregularities, as well as how to use the analytical tools to simplify and streamline the tasks for dealing with those irregularities. Throughout the presentation, I will be showing reports and graphics from the RAM structural system to help illustrate the points being made, but the principles are applicable regardless of the software that you use. Let's begin by first discussing how the codes define and classify irregularities. Some practical approaches to assist in those investigations will be given. I will mostly be focusing on the requirements of ASCE 716, but I will also highlight the requirements of the National Building Code of Canada, India IS 1893, and Eurocode EN 1998. It is informative to see the similarities and differences between our codes. It helps us better understand the issues and enables us to make better decisions on how to resolve or safeguard against the potential problems. While it is important to know the specific code requirements under which we are designing a structure, it is even more important to understand structural behavior and how to plan for it, or better yet, avoid altogether, conditions that might adversely impact the performance of the structure. We will also start out with a discussion of irregularities as they pertain to seismic design. We will discuss wind design later. In ASCE 7, the pertinent section is section 12.3.2, with a requirement to classify the structure as regular or irregular. Corresponding sections in these other codes are shown here. I recommend that you turn to these references according to the code that you design under and follow along as this presentation proceeds. Section 12.3.2 identifies two classes of irregularities, horizontal and vertical. We will begin with horizontal irregularities. This section refers us to Table 12.3-1 for a list of types of horizontal irregularities. They are torsional irregularity, extreme torsional irregularity, reentrant corner, diaphragm discontinuity, out-of-plane offset, and non-parallel system. A torsional irregularity is defined to exist when the maximum story drift at one end is more than 1.2 times the average story drift at the two ends. Therefore, the diaphragm in this example is deemed to be irregular. Be certain to look at story drifts for this calculation, not story displacements. If the diaphragm is classified as flexible, torsional irregularity doesn't apply. An extreme torsional irregularity is like a torsional irregularity, except it is where the maximum drift is more than 1.4 rather than 1.2 times the average drift. In this example, the fourth floor is torsionally irregular, but not extreme torsionally irregular. And again, it doesn't apply to flexible diaphragms. A reentrant corner irregularity is defined to exist where both plan projections of the structure beyond a reentrant corner are greater than 15% of the plan dimension of the structure in the given direction. I want to emphasize both here. Both projections need to exceed 15% of the plan dimension. In this illustration, 4 different conditions are shown. Based on the reentrant corner down in the lower right corner, the diaphragm is not irregular because neither ratio is greater than 15%. Based on the reentrant corners in the upper right and lower left, the diaphragm is not irregular because only one of the 2 ratios is greater than 15%. The lower left-hand corner is especially notable because one ratio is significantly greater than 15%, but because the ratio of the other side of the corner is less than 15%, it is not classified as irregular. In the upper left corner, however, both ratios are greater than 15%. Therefore, this diaphragm is considered irregular. A few configurations are listed for a diaphragm to be defined as having a diaphragm discontinuity irregularity. First, a diaphragm discontinuity irregularity is defined to exist when there is an abrupt discontinuity or variation in stiffness in the diaphragm. This part is subjective and requires engineering judgment. It is probably intended for conditions such as this, among others. A second configuration is one that has cutouts or openings with an area greater than 50% of the gross diaphragm area. This is what that would look like. The area of the opening in this illustration is 50% of the total area enclosed by the outer rectangle. So there would need to be some pretty significant openings before it would be classified as a diaphragm discontinuity under this particular clause. A third configuration classified as a diaphragm discontinuity irregularity is where the effective diaphragm stiffness changes more than 50% from one story to the next. This might occur because of changes in the deck properties, narrowing of the diaphragm, or the presence of openings and cutouts. Using the figure from the previous illustration, one possible approach is to calculate the deflection, starting with the deflection equations for a simple beam as shown. You need to consider both the flexural stiffness and the shear stiffness. In this case, based on those calculations, the diaphragm with a large opening would barely qualify as diaphragm discontinuity irregularity because the stiffness has changed 51% between story A and story B. Roof diaphragms aren't explicitly excluded from this comparison, but I would question the need to classify a structure as having a diaphragm discontinuity irregularity because a roof may have a diaphragm that is 50% less than the floor diaphragm below. Use engineering judgment here. An out-of-plane offset irregularity is defined to exist where there is a discontinuity in a lateral force resistance path that is out of the plane of the frame. That is, where the frames are offset, such as is illustrated. Another example of this is a transfer slab, where a wall sits directly on a slab, but doesn't continue directly below. A non-parallel system irregularity is defined to exist where the lateral frames or walls are not parallel to the global orthogonal axes, as illustrated here. So these are the horizontal irregularities according to ASCE 7. Let's now move on to a discussion of vertical irregularities. This section refers us to Table 12.3-2 for a list of types of vertical irregularities. They are soft story, extreme soft story, weight or mass, vertical geometric, in-plane discontinuity, weak story, and extreme weak story. Two conditions are listed for a diaphragm to be defined as having a soft story irregularity. First, a soft story irregularity is defined to exist where the stiffness of a story is less than 70% of the stiffness of the story above. In this example, the openings at the base of the shear walls reduce the stiffness there such that it is only 68% of the stiffness of the level above, and this structure therefore has a soft story irregularity. Note that every story must similarly be compared to the story above. The second condition is where the stiffness of a story is less than 80% of the average of the 3 stories above. In this same example, the story stiffness at the lowest level is 89% of the average of the 3 stories above, and therefore based on this criterion is not irregular. So by this second measure, it is not soft story irregular because the stiffness is greater than 80% of the average of the 3 stories above, but it is soft story irregular because, as we saw previously, that it has a stiffness that is less than 70% of the level above. A structure is soft story irregular if either condition exists. Again, every story must similarly be compared to the 3 stories above, unless, of course, there are less than 3 stories above the given story. The extreme soft story irregularity is like the soft story irregularity, except it occurs where the stiffness of a story is less than 60%, rather than 70% of the stiffness of the story above. In this example, the change from brace frames to moment frames at the lowest level reduced the stiffness there such that it has only 57% of the stiffness of the level above, and this structure therefore has an extreme soft story irregularity. Or alternatively, an extreme soft story irregularity occurs if the stiffness of the story is less than 70%, rather than 80%, of the average of the 3 stories above. Again, this example is extreme soft story irregular. The weight or mass irregularity is defined to occur where the mass of any story is more than 150% of the mass of an adjacent story. Note that in this case, the roof is explicitly exempt from that comparison. The vertical geometric irregularity is defined to occur where the horizontal dimension of the frames or walls of any story is more than 130% of that of an adjacent story. The in-plane discontinuity irregularity is defined to occur where there is an in-plane offset of the frame that results in overturning demands on the supporting frame members, such as a transfer girder situation. The weak story irregularity is defined to exist where the strength of a story is less than 80% of the strength of the story above. Note that this is different than the soft story irregularity, which is based on the stiffness rather than the strength of the stories. This determination is made by summing up the lateral strength of all of the frame members that resist the story shear for the direction of the seismic force under consideration. For shear walls, sum up the shear capacities of the walls aligned with the direction of the seismic force. For brace frames, sum up the horizontal component of the brace axial strengths and the shear capacities of the columns. The code does not explicitly state that the strength intended for inclusion here is only the shear strength. In a moment frame, the column and beam flexural strength also resist the story shear. It seems reasonable to assume, though, that the intent for moment frames is to sum up the column shear strengths, but I might be wrong on that. The member shear, flexural, and axial strengths can easily be obtained, so use your judgment. So based on the appropriate member strengths, get the sum for each level, and if the strength of any level is less than 80% of the level above, the structure is classified as weak story irregular. The extreme weak story irregularity is like the weak story irregularity, except it occurs when the strength of a story is less than 65% rather than 80% of that of the story above. The process of summing the story strength is the same, and if the story strength is less than 65% of that of the story above, the structure is classified as extreme weak story irregular. So these are the vertical irregularities according to ASCE 7. In the definition of vertical irregularities, there are 2 important exceptions. The first is that if no story drift ratio is greater than 130% of the story above, types 1A, 1B, and 2 do not apply. In the determination of these drifts, the 5% accidental torsion does not need to be applied. Note that that is different than when investigating the drifts for horizontal torsional irregularity, which requires the inclusion of the 5% eccentricity. Also, this drift ratio comparison here is not required for the top 2 stories. These comparisons can be easily made by only considering the non-eccentric load cases and comparing the resulting drift ratios. The second exception is that irregularities 1A, 1B, and 2 do not apply for one-story buildings, nor do they apply for two-story buildings in seismic design categories B, C, or D. For the next few minutes, let's briefly review the corresponding requirements in the Canadian, Indian, and Eurocodes. By understanding how others treat the topic of structural irregularities, we can better understand our own code, and we can better understand structural behavior. This won't be an exhaustive treatment of these codes. We will start with the National Building Code of Canada. The requirements can be found in section 4.1.8.6, especially table 4.1.8.6. The corresponding ASCE 7 classification is indicated here with differences where they occur highlighted. Type 6 is analogous to ASCE 7 vertical type 5, but it differs in that it explicitly identifies the shear strength as the strength to consider in the classification, and it classifies a story as a weak story if its strength is less than that of the story above, whereas ASCE 7 allows the strength to be 80% of that of the story above. Type 7 is analogous to ASCE 7 horizontal type 1, except that the drifts are determined considering a 10% eccentricity rather than a 5% eccentricity, and the limit on the ratio of maximum drift to average drift is 1.7 instead of 1.2. Note that there is nothing analogous to the ASCE 7 horizontal type 2 or 3 irregularities, nor does it classify any as extreme. The Canadian Code does have type 9 gravity-induced lateral demand irregularity, which is unlike anything in ASCE 7. Roughly explained, and for the more usual framing configurations, if the horizontal shear induced by the gravity loads exceeds 3% of the shear resistance of the frames, the structure is irregular. Gravity loads don't normally produce significant lateral shears, but if they do, they need to be compared with the capacity at each story. Let's now turn to India IS 1893. The definition for plan irregularities is given in Table 5. Number 1 is a torsional irregularity. It lists two conditions that must occur. For the first, it requires the comparison of the maximum drift to the minimum drift rather than to the average, but if you work through the numbers, you will see that this is identical to ASCE 7 1A. The second condition is that the fundamental torsional mode has a longer period than the fundamental translational modes. Here, for example, we see that the first mode of this structure is a torsional rather than a translational mode. From the results of an eigenanalysis, we see that this structure falls within the description of the second item, that is, the first mode is a translational mode. So, if the ratio of the maximum drift to average drift exceeds 1.5, and if the torsional mode is a lower mode than either of the fundamental translational modes, it is torsionally irregular. The second irregularity is reentrant corners. It is analogous to ASCE 7, except ASCE 7 is less onerous in that it is based on both plan projections, not just one direction. The third plan irregularity is for slabs having openings greater than 50% of the full area. This is the same as ASCE 7, except there's nothing about the change in stiffness. Out-of-plane offsets is the same as ASCE 7. Non-parallel lateral force systems is also the same as ASCE 7. The definitions for vertical irregularities is given in Table 6. The first is soft story. It is the same as the Canadian Code and is similar to ASCE 7 vertical type 1, but differs in that it classifies a story as a soft story if its stiffness is less than that of the story above, whereas ASCE 7 allows the stiffness to be 70% of that of the story above. Number 2 is mass irregularity. It is similar to ASCE 7, except it only requires the comparison to the story below, and it doesn't exclude the roof. Number 3 is vertical geometric irregularity. It is similar to ASCE 7, but with a limit of 125% instead of 130%, and only requires the comparison to the story below. Vertical irregularity number 4 is in-plan discontinuity. Similar to ASCE 7, except ASCE 7 classifies any offset that creates overturning as irregular. Number 5 is weak story. Similar to ASCE 7 vertical type 5A, but differs in that it classifies a story as a weak story if its strength is less than that of the story above, whereas ASCE 7 allows the strength to be 80% of that of the story above. Number 6 is floating or stub columns. These are columns supported by a transfer girder. This would fall under ASCE 7 in-plane discontinuity. Vertical irregularity number 7 is irregular modes of oscillation, in which the modes have two characteristics here. There is no analogous type in ASCE 7. Starting at the bottom of the report shown here, the modal effective mass factors list the total percent of mass included for each mode, and in this case the third mode only includes 64.39% of the mass in the y direction, which is less than the limit of 65%. The modal direction factors indicate that the second mode is the fundamental mode in the y direction, and the third mode is the fundamental mode in the x direction. The difference in the periods between the second and third modes is 0.7532 seconds, which is less than 10% of the larger, so this structure is not irregular for modes of oscillation. Now the Eurocode. As we saw, the Canadian and Indian codes were very similar to ASCE 7. The Eurocode is very different. Section 4.2.3 addresses structural irregularity. Section 4.2.3.2 lists the definitions for regularity in plan. The Eurocode defines all of the conditions that a structure must satisfy in order to be considered regular, rather than listing any conditions that would make it irregular. This requirement is subjective, requiring that the stiffness and mass be distributed approximately symmetrically. Item 3 is that the floor layout be compact, that is, that it not have any significant reentrant corners or setbacks. To determine this, a convex polygon is drawn around the floor outline. Then the areas of the reentrant corners and setbacks are calculated. If the area of any of these corners or setbacks exceeds 5% of the floor area, the floor is not compact, which means the structure is not regular. Note that this differs from ASCE 7, which uses dimensions rather than area. A1 in this example is about 3%, so not irregular per Eurocode, but recall that it is irregular per ASCE 7's definition. The fourth item is also subjective, the intent of which is to eliminate buildings with distinct wings from consideration of regularity. It requires that the diaphragm stiffness be sufficiently large compared to the stiffness of the frames, such that the diaphragm deformations have little impact on the distribution of the forces to the frames. The fifth item limits the aspect ratio of the floor plan to 4 in order to be considered regular. Item 6 is a measure of the susceptibility to torsion and the ability to resist that torsion. It is a function of the mass properties, the offset of the center of mass from the center of stiffness, and the torsional stiffness. These values can be obtained from the structural model. Section 4.2.3.3 lists the definitions for regularity and elevation. Again, the Eurocode defines all of the conditions that a structure must satisfy in order to be considered regular, rather than listing any conditions that would make it irregular. Item 2 requires that frames and walls are continuous. This is analogous to ASCE 7 in-plane discontinuity criteria. Item 3 requires that there are no abrupt changes in mass or stiffness between stories. This is subjective, but related to ASCE 7 soft story and weight mass. Item 4 requires that there are no abrupt changes in the strength between stories. Again subjective, but related to ASCE 7 weak story. Item 5 shows the limits to the extents of setbacks. It is interesting to see the similarities in the definitions of irregularities between these codes. To me, it is even more interesting to see the differences. It illustrates that these requirements are to a degree subjective. different experts have different opinions on the matter, with each code indicating what the various code authors felt was important. So far, we've been discussing the classification of irregularities as they relate to seismic analysis and design. Most codes only address the classification of irregularities for seismic applications and have few, if any, requirements related to wind. ASCE 7 has only this definition of a structural irregularity related to wind. It states that a building is torsionally regular when the maximum displacements at each story from the torsional wind load case, case 2, does not exceed the maximum displacement at the same location for the regular wind load case, case 1. So in this example, looking at the displacements, not the drifts, at the roof, the displacement in the x direction for the regular load case is 0.8144 inches, which is greater than the worst of the displacements for the torsional load cases at the same location, 0.7238 inches. This would indicate that the structure is regular, although you need to repeat this for all stories and look in both the x and the y directions. In this case, the deflection in the y direction for the regular case is 0.6056 inches, but the worst deflection in the y direction for the torsional cases is 0.8766 inches, so this structure is not regular for wind. That is about it for the definition of irregularities for wind. It seems that they are less of a concern for wind than for seismic behavior. So after going through this process of identifying structural irregularities for wind and seismic, how is analysis and design affected? What is required by code if a structure is identified as irregular? The impact on analysis and design procedures is substantial. Design requirements are more onerous, and in some cases, certain structural configurations are prohibited. This topic will be discussed in detail in the second part of this two-part webinar series on structural irregularities. So why does it matter? Why is there so much emphasis on structural irregularities? From the ASCE 7 commentary we read, earthquakes have shown repeatedly that buildings that have irregular configurations suffer greater damage. The image on the left shows an example of a soft story or weak story irregularity. The bottom story is destroyed while the stories above seem relatively unaffected. The image on the right is an example of an in-plane discontinuity irregularity. The ASCE 7 commentary elaborates. In irregular structures, inelastic behavior can be concentrated by irregularities and can result in rapid failure of structural elements in these areas. Remember that during a severe earthquake, the frames are expected to deform inelastically. This inelastic demand is expected to be shared by all of the frames. However, just as discontinuities or notches can cause stress concentrations on a small scale on a plate or a part, structural discontinuities and changes in stiffness in a structure can cause inelastic demands to be focused on members in those areas. This may cause these members to fail well before the rest of the seismic force resisting system is fully engaged. Some irregularities introduce unanticipated demands into the structure. An example of this would be torsional irregularities. When a structure is susceptible to twisting, that behavior may be amplified in an earthquake, resulting in shear forces due to the rotation adding significantly to the direct shear forces. The elastic analysis methods typically used often do not predict the distribution of earthquake demands in an irregular structure very well. The code generally allows for an elastic analysis, but seismic behavior is inelastic. So the analysis methods often don't identify areas in the structure that are vulnerable due to the irregularities. For these reasons, it's necessary to identify structural irregularities and to design for their impacts accordingly. I would like to take a break now from the discussion and give a demonstration of how software can be used to simplify the task of identifying these structural irregularities. The program that I will be using is the RAM structural system, and at the conclusion of the demo, we'll return to the discussion and end with some conclusions and some recommendations. The RAM structural system model contains the model of the entire structure. That includes the masses, the mass moment of inertia, center of mass, and eccentricities specified by the user. And this can be the 5% eccentricity required by ASCE 7 or the 10% required by the Canadian code. And these weights and masses are automatically calculated from the model. Load cases can be very quickly generated. For example, we can create an eigen-solution load case for getting the periods and the modes merely by specifying the number of periods that we're interested in including. A center of rigidity load case can also be created, and we'll take a look at that in a moment. We can also create the seismic load cases where we can specify whether or not that those eccentricities are to be included. We can specify the other important information, including whether or not to specify that the drift requirements be used in the calculation of the forces. Also generate a wind load case here. After the analysis is complete, we can investigate the results. Let's start out by taking a look at the drift, where we can take a look at the drift at these control points that have been set up for the load cases that have been specified. And we see that in this report, at the given location for the given story, in this case, the drift seismic load cases, we can see the displacements, the story drifts, and the drift ratios at this location. And we can compare these values with the results at other locations on the structure, for example, the extreme ends of the structure. And from these values, we can determine whether or not there is a torsional irregularity. Let's next take a look at the centers of rigidity report. In this report, we see a printout of the centers of rigidity and the centers of mass, which are necessary for the Eurocode implementation. We also see a listing of the story stiffnesses at each story for both the X and the Y direction, and from these we can determine whether the stiffness above or below a story has changed more or less than the code requires. We can also take a look at the masses as we saw a moment ago, and we can determine if there's a mass irregularity based on whether the mass has changed. And likewise, we can take a look at the criteria mass and exposure data report and see that same information. And so again, from this, we can determine if there is a mass irregularity. Let's next take a look at the mode shapes. So here we see mode number 1, and it obviously is a rotational mode. Mode number 2 is a mode in the lateral Y direction, and mode number 3 is a translation in the lateral X direction. And we can look at the mode shapes for any mode that we want to consider. Let's next look at the periods and modes report, which gives us the periods for each of the modes, where we can tell how closely coupled or how well spaced out they are. We can look at the modal participation factors, which identify what direction a particular mode is in, whether it's X, Y, or rotation. And the modal direction factors are even more helpful for that. We can see what proportion of a direction a given mode moves in. And then we can look at the modal effective mass factors and identify what percent of the mass has been included in a given direction to verify that the appropriate percent of mass has been used in the analysis. And then we can investigate the member capacities so that we can determine if there is a weak story irregularity. And so, for example, we can look at the column. We can very quickly see what the moment capacity or what the shear capacity is for that column. And similarly, we would look at the axial capacities for the braces and so forth to determine the story strength. Now we can likewise go into RAM concrete and in particular the shear wall module, where we can look at the shear strength of the concrete walls. So we can select the section of wall that we want to obtain the values for. And looking at the report, we can see what the shear capacity is for that section of wall. So there are a lot of tools available in the RAM structural system to assist in the investigation of structural irregularities. Recognition of irregularities and their impact on structural behavior is crucial to the safe and appropriate design of the structure. Proper application of building code requirements depends on the proper determination of these conditions. As we have discussed, there are two types of irregularities specifically identified in the code: horizontal and vertical. In ASCE 7, structures in seismic design category A are exempt from all requirements related to seismic structural irregularities. Category A represents very low seismic conditions. In ASCE 7, structures in seismic design category B and C are exempt from most requirements related to vertical irregularities. This will be discussed in greater detail in the second presentation on structural irregularities. Table 12.3-1 and Table 12.3-2 provide a convenient checklist of the irregularities and when they need to be investigated. Both seismic and wind design is impacted. Although the code requirements explicitly address seismic design in much more detail, keep in mind that a structural irregularity could impact the performance of the structure under any loading condition. The impact of irregularities can be significant. Inelastic behavior may be concentrated by irregularities, resulting in rapid and premature failure. There may be unanticipated demands. Our usual analysis methodologies are often not good at predicting the distribution of seismic demands. The design may be significantly penalized when a structure is deemed to be irregular, as will be discussed in greater detail in the second presentation in the series on structural irregularities. And finally, while it is possible to determine the presence of these irregularities and to modify the analysis and design to account for them, it is much better to modify the structural configuration to eliminate them if possible. A structure without these irregularities is much more likely to perform better in an earthquake. I hope this presentation has been useful. This is the first of a two-part series on structural irregularities. This one is on identifying structural irregularities. The second will be on dealing with structural irregularities. More information on this and other technical topics related to structural analysis and design can be found on Bentley Communities. There's also a Bentley Structural channel on YouTube. Thanks for watching.